Hi, my name is Nina Shafiqah binti Sanusi and my project is entitled Transforming Agriculture Waste into Sustainable Skincare. My supervisor for this project is Mr. Muhammad Izzuddin Samri. Did you know that the rubber tree is Malaysia's second largest plantation crop after palm oil? While we all know about rubber itself, the seeds are usually just thrown away even though a single plantation can produce 800 to 1,200 kilograms of seeds per hectare every year. What's even more exciting is that these little seeds are packed with fatty acids that are amazing for the skin. Yet, most research so far has only looked at using them for industrial purpose like biodiesel. This means there's a huge opportunity to explore and create exciting new skincare products from them. This reflects the spirit of building a resilient nation. My project aims to transform agriculture waste through sustainable extraction in line with SDG 12. I also work to develop and characterize a high-quality, safe and effective cream that support health and well-being reflecting SDG 3. Finally, I seek to introduce a patentable skincare innovation for national resilience in line with SDG 9. Let's take a look at the material and method. First, the rubber seeds were collected, the shells were removed, the kernels were chopped and oven dried. For the extraction, two methods were used. In the hot compression method, 250 grams of dried kernels were pressed using preheated automatic oil compressor. In the sauce-like extraction method, dried rubber seed kernels were blended to reduce particle size. It was then extracted with hexane and the solvent was later removed using a rotary evaporator. Sauce-like extraction produced a significantly higher yield compared to hot compression. Now, let's take a look at oil analysis. First, in the organoleptic evaluation, the hot compression oil appeared darker and thicker, while the sauce-like oil was lighter and clearer. Both, however, had a strong pungent smell. From the FAME analysis, the sauce-like oil showed higher amount of omega-3 and omega-6, but it also had higher free fatty acid, which made it less stable. In contrast, the hot compression oil contained more omega-9 and saturated fat, supporting skin hydration and softness. Thirdly, when we look at peroxide value, the hot compression oil recorded a much lower value, meaning it had stronger oxidative stability and therefore a better cosmetic shelf life. For viscosity, the hot compression oil was thicker, giving it richer texture that helped to protect our skin barrier. And finally, when we measured density, specific gravity, and refractive index, all were higher in the hot compression oil, indicating heavier and more stable lipids that provide durability and long-lasting effect. Next, for antimicrobial activity tests, these are the bacteria tested using the diffusion method. Both oils inhibited Staphylococcus aureus, while hot compression oil showed stronger dose-dependent activity against Propionibacterium acnes, which is the main acne-causing bacteria. Both oils have no effect towards Staphylococcus epidermidis, which is good as it helps to preserve the skin's natural protective flora. I prepared the cream using hot compression rubber seed oil. So here are the formulation which combine water and oil-phase ingredient, preserved with phenoxyethanol and scented with melon fragrance. I use this marketed cream as a comparison since grapeseed oil and rubber seed oil share similar fatty acid profile. Can you guess which one is my formulation? Here is the answer. Now, let's move on to the characterization of the formulated cream. All tests were carried out under preliminary accelerated stability testing for 4 weeks following ICH guideline. The centrifugation test showed no phase separation. The cream also maintained a smooth texture, yellow to off-white color throughout the study. The pH stayed within the safe skin range of 4.5 to 6.5, while the zeta potential remained strongly negative, indicating strong electrostatic repulsion and good emulsion stability. Spreadability stayed stable and good coverage on the skin compared to marketed cream. Next, the cream showed stable non-Newtonian shear thinning behavior where viscosity decreased and shear rate increased. This means it resists flow at first but spread smoothly under stress, while it stayed thick enough at rest to prevent dripping. Droplet size showed a sharper peak, indicating a better uniformity and long-term emulsion stability compared to the marketed cream. For the microbial contamination test, we followed USP and Asian guidelines to make sure the cream is safe. No microbial growth was observed at week 0 or week 4, and counts remained below USP and Asian limits, confirming microbiological safety. Overall, the rubber seed oil cream remained stable, safe, and effective, showing strong potential for cosmetic use. In developing our innovative product, we faced several key challenges. First, trial and error. Developing the cream required many attempts and changes in formulation to achieve the most stable and high-quality product comparable to the marketed cream. Secondly, raw material challenge. The rubber seed oil extraction was conducted during the off-season when the seeds were still immature and had not yet fallen, making it challenging to collect a sufficient quantity for both analysis and cream. And thirdly, collection difficulty. The study was conducted during the rainy season, making it hard to collect enough rubber seed. Further analyses are required to ensure the safe and efficacious use of rubber seed oil in cosmetic creams. For example, a cosmetic product efficacy study and a patch test irritation study on human panelists should be conducted. In conclusion, my innovation transformed discarded rubber seeds into a safe, beneficial skincare cream, turning waste into value while supporting sustainability and a resilient nation. That is all from me. Thank you.